Greetings, M Squared here, and today we're going to talk about functions. So yesterday we talked about domain and range, and you should have learned about functions in 8th grade. So this is kind of a prerequisite for what we're about to do. It's not really one of our learning targets, but you kind of need it to do the learning targets that we're going to talk about. So we're going to talk about functions. How do you know if something's a function? We're going to figure out how you know if it's a table, a graph, or a set of points. So a function is just a relationship between what goes in and what comes out. So I think of it like a machine. Have you ever put something in a machine and received something different out of the machine? So yeah, so you can put your ATM card in the machine and it gives you money, right? You can put $1 in the vending machine and you get out a bag of chips. So we all know that there are real life examples of when we put something in and we get something different out. So we have an input, and the input is also our domain. We talked about domain and range, and then we put it in a machine and we get something else out. That's the output, and that's going to be our range. So it's important to know that it's just some kind of transformation, that you put something in, you get something out. Now you could theoretically get the same thing out, right? We know that that's true too. The vending machine could reject your $1. And so sometimes when we put a number into some kind of function, it doesn't change. But just so you know, we're going to put something in, we're going to get something out. So review from yesterday, a relation is a set of points, and a function is a relation. Okay, so if that means a function is also a set of points, but there's a condition on it. Each input has to have exactly one output. Or we would say that each domain value has to have exactly one range value, or each x has to have exactly one y. Whichever way you want to put it. I like the x and y thing. Every x must have exactly 1, not 2, not 0, not 17, exactly 1 y. Does each y have to have exactly 1 x? No, it does not. It's about x and going to 1 y. So it's really important that we look at x and make sure we don't have the same x going to two different y's. So a good description of it is this notation right here. You see it kind of like a cursive F. It's a little italicized, not really cursive, a little italicized, and it's an F, and then a parenthesis with an X inside, then an equal sign, and a 2x plus 3. So this F part is the name of the function. It's not always F. It could be G, H, could be lots of things. But if it's F, then what we say is F of X, whatever our input is. If our input changes, if it was a 3, we'd say F of 3. If it was a Y, we'd say F of Y. Whatever that might be, it's F of X. So our function name, whatever the input is, then equals 2x plus 3. So this is a description and how you read it. F of X equals 2x plus 3. That's how you would read it. So our function is just like a rule, kind of like a machine, right? So here's our rule, 2x plus 3, and here are some numbers we're going to put in. So if we're going to put a 0 in, that means we have to find F of 0. That means we take whatever 0 is, we put it in for X and see what we get. So you'll notice that the 0 here, you put it in for X. 2 times 0 plus 3 is 3. You put the 1 in because now you have to find F of 1. So F of 1 is 2 times 1 plus 3, which is 5. F of 4 is 11. Now, what if I just wanted to put a different variable? I wanted my input to be n instead of x. Then I would say 2n plus 3. That really should, to me, be 2n plus 3. Because that's what you get. You get a y value, but you're getting the 2n plus 3. Okay, so function. Every x has to have exactly 1 y. So when we look at this, there's different ways you can do it. So this is kind of like a little, I don't know what you want to call it, little machine where every one of these dots has a little arrow going to another one. So we want to make sure that every x has exactly 1 y. So we see that x, it goes to exactly 1 y. This x goes to exactly 1 y. This x, exactly 1 y. This x, exactly y. This x, exactly 1 y. It doesn't matter if they go to the same y, but they have to go to exactly 1. There can't be 2 arrows coming off the x. Each element in the domain, or input, must have exactly 1 in the output. So now we're going to give you examples of what that would look like. Function or not a function. So this is a function because every x is going to 1 y. This is not a function because this x right here is going to 2 different y's. So we say that is not a function. Function, not a function. Okay, what if it was a table? For a table, we have to look at the x's. Do you see how all the x's are different? If all the x's are different, then they each have exactly one y. It's when you have two x that are the same, for example, right here, I have two 1s and they're going to two different things. So it's kind of like up there when you had the two arrows coming off of the domain. So I have 1, 4 and 1, 8. So this is not a function because I have the number 1 going to two different y's. Also, the number 2 is also going to two different y's. So this would not be a function. Okay, now we're going to look at a graph. So at a graph, our x's are like this. Our x's are going left to right. So if I go over here, let's say that's 3, and I go up, how many y's did I hit? I just hit 1. Over here, if I go to this number right here, what 1, 2, 3, 4, 5, 6, 7. If I go to 7, I'm hitting the graph 3 times. That means the answer is right here, 7. This is like 7, 3, 7, 5-ish, 7, 9-ish, whatever. You'll notice that I have 7 going to 3 different y's. Not a function. Yes, it's a function. And this is what we call a vertical line test. If you have a graph, the easy way to tell if it's a function is to just draw some vertical lines. And if there's ever a vertical line that crosses more than one time, it is not a function. Okay, we're going to talk about two different kinds of domain now. We have a continuous domain and we have a discrete domain. Let me put those up there. That's another thing you need to know. So I'll zoom out a little bit. So domain is the x values. So a continuous domain means that there's little arrows and it just goes on forever. But it also, even if it was 2 points, it would still go on without picking up the pencil. So if I could draw without ever picking up the pencil and keep on that graph, then it's continuous. It's discrete if I have to jump, so I can't just draw a line there. So these two things are discrete. Now, there's different things in life that would be continuous and different things in life that would be discrete. We're going to talk about those two examples. But domain includes all real numbers in a set. So all the real numbers forever and ever are included in that set, whereas this domain, it has individual numbers. So those would be separated by commas, is what we did the other day. And so the picture would look like a graph or a curve without any holes in it. And this one would look like a graph of just individual points. And here are some examples. So if you had a hose and you had to fill up your swimming pool, it was 10,000 gallons, you would put the hose in and it would fill up at a constant rate. So at any point of the minute, at any minute of the day, you would have a certain amount. It doesn't just go exactly from 10 gallons to 11 gallons. There's a point in between where it's between 10 and 11. So it's a continuous fill up. Versus if I was talking about the number of tables and chairs, and I said, it says a restaurant needs to order chairs and one table can accommodate 4 chairs. So I'm not going to have 3.5 chairs. I'm not going to have 1.5 chairs. That's not going to fit, right? I don't say, oh, here's a half a chair, let me put it at the table. So that's a discrete function where you're just talking about certain numbers. So anytime you're talking about people, we usually don't have halves of people or halves of chairs or halves of tables. That would rarely count. So we need to make sure that we know the difference between discrete and continuous because that helps us with our domain. Now we're going to do some examples. So I'm going to cover those up. So we're going to ask ourselves, is it a function or not? And is it continuous or discrete? So, 2 things. Is it a function? To find out if it's a function, I look at x's. Are any of the x's the same? Yes, those 2 are the same, and these 2 are the same. What does that mean? It's not a function. If it was, it would be discrete because it's just a bunch of points, but it's not a function. Let's zoom in a little bit. Okay, so this right here, it's a solid line. It's going forever. Does my vertical line test work? So I make a bunch of vertical lines and it never crosses more than once. That means yes, it's a function. Is it continuous or discrete? Since there's no holes in it and I can go from here all the way over there and never lift up my pen, it's a continuous function. The domain is continuous, I should say. Okay, is this a function? So I test with my vertical line if it's a graph. It crossed twice. That means it's not a function. Okay, over here. I look when I have a table again, I look at my x's. Are all the x's different? If all the x's are different, then it's a function. Yes, it's a function. Is it discrete or continuous? Well, it's discrete because it's just listing pairs, so that would be a discrete function, or I would have a discrete domain. Okay, here's another table. So I look at my x's. I see 2 8s. Doesn't even matter if there's 2 2s. If there's 2 8s, it's not a function. Vertical line test? Yep, it works. They only cross once, so yes, it's a function. And because it's a graph, we say it's continuous, because I can just draw that whole thing without lifting up my pen. Okay, function or no function? Not a function, because it crossed twice. Function or no function? Well, it's not a function. Because look, it is a vertical line, and if it's a vertical line, that means one x has all these y's. So this is not a function. Function or no function, vertical line test works. Yes, it's a function, and yes, it's continuous. Because I can go from here to here and never lift up my pen. There's no holes. Okay, 2 more things, and then one more thing, actually. Okay, here we go. What number could you add to this relation to make it remain a function? Because currently it is a function. And what number could you add to this relation to make it not a function? So there's a lot of possibilities here. There are an infinite number of possibilities that you could put there for the first one. How could you make it stay a function? You just have to avoid 3 numbers, -4, -6, and -8. Any other number you put there will make it a function. So for this one, we'll just say 5. But you could say 1, 2, 3, 0, 4, -5, -7. You just can't say those 3. And then for this one, there's only 3 choices. It's either -4, -6, or -8. Because if you change this to make it so that it is the same as one of the other x's, then it makes it not a function. So hopefully you know a little bit more about functions, discrete and continuous functions. Good luck. M² signing out.